Okay, so hello everyone. Welcome to our weekly TCS seminar. This time we have Tung Nguyen from University of Oxford. Tung has done a lot of research. He did his PhD in Princeton with Paul Seymour. He's known for his research in Erdős Hajnal, related to Erdős Hajnal conjecture, asymptotic structure, and most recently, very exciting result about polynomial 𝜒-boundedness for P5 free graphs, and this is what Tung is going to tell us today about.
So thank Bartosz for the very kind introduction. So thank you very much for coming. Thanks for having me here. It's actually my very first time in Poland, and it's actually a very great opportunity to come here and not just to work with nice people and also to visit the city. Krakow, for me, is a very, very nice city. I'm still exploring with a lot of sightseeing. Anyway, before going to the talk, I would like to acknowledge the support of my current two affiliations in Oxford. So first of all, that's the Maths Institute, and second is my college, Christchurch. They have been immensely helpful and supportive during my first couple of months in UK in Oxford. And so this result is done mostly through the support of these two affiliations. Okay. Right, so this result is about excluding induced graphs and chromatic number and clique number. And before I move on, I just wanted to make sure that we're on the same page. So in this talk, all graphs are finite, and I will always fix a finite graph G, and I will use chi G and omega G respectively to denote the chromatic number and the clique number of G. Okay, and of course we know very well from basic graph theory that chromatic number is always at least the clique number. And if you have a graph G with large chromatic number, then perhaps one of the most obvious reasons why G can have large chromatic number is just because it contains a large clique, right? And so it is kind of natural to ask the question in the other direction, which is, if you have a graph with a large chromatic number, then do you always have a large clique? And then, of course, the answer is no, and that is very classical. There are so many constructions of triangle-free graphs with arbitrarily large chromatic number. So I list the three most well-known examples here: construction by Tutt, by Michalski, and by Zykov, and so on. And I actually intentionally chose these three because they probably figure out they were done before MDFS was born, I think. So this was from a long time ago, and people already knew about graphs with large chromatic number and with no triangle. Right. So a very fundamental pursuit of graph theory is to try to understand what's going to happen if you have graph with large chromatic number and with bounded clique number. If you have a graph or a class of graphs where the chromatic number grows arbitrarily fast compared to the clique number, then what can you say about its local structure? The point here is that both chi and omega are very global graph parameters. And a theme in graph theory in the past couple of decades has to try to understand local global properties and interactions in graph theory. And so in this talk, I will try to restrict my attention to the local containment called induced subgraphs. So for two graphs, G and H, I'll say that H is an induced subgraph of G if H can be obtained from G just by removing vertices. And the rule here is that you have to maintain the pattern of the edges and the non-edges among the remaining vertices. Okay. And in this talk, for the sake of brevity, I'll say that a class of graphs is just a class closed under taking induced subgraphs. So whenever I have a graph G in the class, then every induced subgraph H of G is also going to be in the class. Okay. And for two graphs H and G, I'll say that G is H-free if it contains no H induced subgraph. So from these definitions, you can see that if H is very, very tiny compared to G, then being H-free is a purely local property. Okay. Right. And the study of classes of graphs with chromatic number a lot larger than clique number was put forth by Gyárfás from 1985, so 40 years ago. And we say that a graph class G is time-bounded if there is some function f such that the chromatic number of every graph in the class G is bounded from above by the function f of the clique number of that graph. Okay? And in this case, I'll say that f is a chi-binding function for this class G. Okay. Oh, by the way, just a small remark. If you have any question, then please interrupt, and I will try to answer as well as I can. Okay. And going back to this definition, so this is a formal way to capture classes of graphs with chromatic number bounded from above by some function of the clique number. And of course, if a class G doesn't have this chi-boundedness property, then you know that chi grows arbitrarily fast in terms of omega. And this notion was introduced in the paper Problems from the World Surrounding Perfect Graphs by Gyárfás. And there he introduced this notion together with a lot of interesting questions surrounding this notion. And the title is kind of suggestive, right? It suggests that this notion was partly motivated by the notion of perfect graphs. And just in case you haven't known, the class of perfect graphs is a class where you have that chromatic number is equal to clique number for all induced graphs. Okay. In other words, the class of perfect graphs is chi-bounded with identity chi-binding function. Okay. So chi-boundedness is a way to generalize perfectness. And whenever we talk about perfect graphs, perhaps we should talk about the strong perfect graph theorem of Chernovsky, Robson, Seymour, and Thomas from 25 years ago. And this says that a graph is perfect if and only if it contains no odd hole and no odd anti-hole. And here, a hole is an induced cycle of length at least 5, and an anti-hole is a complement of an induced cycle of length at least 5. So no odd anti-hole and no odd hole just means that you don't contain any odd cycle of length at least 5 as an induced graph in the current host graph or in this complement. Okay, and there is an if and only if characterization of perfectness. And it is a very nice example of the fact that you can characterize some chi-bounded class in terms of forbidden induced graphs. Okay. Right, but there is just one result. I mean, even though this was already one of the nicest results in mathematics recently, there is just one result falling into the broader program of chi-boundedness. Because here, in chi-boundedness, we are actually more interested in how chromatic number is going to be bounded by some function of the clique number, and not just an identity function. Okay. And there are still many interesting open questions left in this program. And perhaps the most important open question is the Gyárfás-Sumner conjecture, which was independently posed by Gyárfás and Sumner in some 40 or 50 years ago. And what it says is, if you give me any tree T, then the class of graphs with no induced T is going to be chi-bounded. Okay? And this one is open and very much open. And the idea here is that if it's true, then it will be an if and only if a necessary and sufficient characterization of forest. Because Erdős in 1959 proved that graphs with large chromatic number and with no short cycle, or in other words, with high chromatic number and with high girth. And the construction was done by taking a sparse random graph, as probably all of you already knew about. And so there are many such graphs, and the intuition here is that there are actually graphs with arbitrarily large chromatic number and locally tree-like. In a sense that if you pick any vertex in the graph, and then you try to zoom in the border bounded radius around that vertex, then what you see is just going to be induced trees and nothing else. And what Gyárfás-Sumner predicts is basically the converse of this. And it says that perhaps in such graphs, all copies of small induced trees must appear in these graphs. Okay. Yeah, but of course it is still very much open. And so far we have known we have known about some confirmed cases of this conjecture. And let me just try to summarize some of them. So first of all, when the tree T is this star K1T, which is this configuration, one vertex adjacent to T vertices pairwise non-adjacent. This was done by Gyárfás when he introduced the notion of time-boundedness. But we can easily see through Ramsey's theorem, for example, that if you don't contain a K1T as an induced subgraph, then your match degree is going to be bounded by a polynomial function of the clique number. And so the graph has bounded chromatic number, right? And a little bit harder is the case when the forbidden tree T is the path PT, which is this path on T vertices. And this was done also by Gyárfás in the same paper. It's actually when he introduced the method of what is known as the Gyárfás path argument. And the argument gives an exponential bound like this. So the chi-binding function is going to be t minus 2 to the x minus 1 if we try to optimize his argument. Right, and the three harder and more difficult cases are, first of all, subdivided stars by Alex Scott in his PhD thesis. And the key point here is that actually Alex, in his thesis, proved the Gyárfás-Sumner conjecture if you exclude all induced subdivisions of any given tree T. So not just the tree T itself, but all of its subdivisions. And the point here is, if you are given a subdivided star like this, then you can easily see that any subdivision of this subdivided star is going to contain itself as an induced subgraph. And so this subdivided star result follows. Right? And then the case when the forbidden tree T is a tree of radius 2, and this was done around the same time by Kieset and Penrice. And a little bit harder, done for some trees of radius 3 by Kieset and Zhu a couple of years later, and then extended more by Scott and Seymour more recently in 2016. So the point about the last two results is something like this. So for Kieset and Zhu, the key point here is that these trees of radius 3 are obtained from these trees of radius 2 by subdividing each edge adjacent to the root exactly once. And the point here is you have to subdivide every single edge adjacent to, every single edge incident to the root. But what Scott and Seymour did was, you could choose any number of edges incident to the root that you like, and then you subdivide them. So so the Scott-Seymour result is a bit more general than the Kieset-Zhu result. But these two don't quite cover all trees of radius 3. And as far as I know, it is still very much open. Gyárfás-Sumner is still very much open when the forbidden tree T has radius 3. And perhaps I can say a little bit more about the difficulty. That is when you have quite a few vertices of degree at least 3 sufficiently far away from each other, and somehow all of the current known methods break down. So likely, at least in the case of trees of radius 3, we would have to come up with a completely new method, which is remain to be explored. Okay, right. So so as you can see, for the first two cases for stars and paths, I try to list also the chi-binding functions coming from the proof. The first one is polynomial, and the second one is exponential. The reason I didn't say the chi-binding, I didn't talk about the chi-binding function in the last 3 cases was just because the proofs give very, very fast-growing functions. Not just exponential, but super exponential. So layers of exponential. And I'll actually go back to this issue later. I will try to explain a bit more why we are in this situation. But of course, for Gyárfás-Sumner and given that we already know that we can get a polynomial bound for stars. Perhaps a very natural question is that whether you can improve the chi-binding functions. And if you can improve it, then whether you can get to the actual polynomial bound. Right? So, and this is actually the motivation for polynomial chi-boundedness. So I say that a class of graphs which is chi-bounded is polynomially chi-bounded if I can choose a polynomial chi-binding function for this class. So in other words, the optimal chi-binding function for the class has polynomial growth. Okay. Yeah, so this has been a pretty active business in the area for the past 10 or 15 years. And of course, given Gyárfás-Sumner, it is kind of natural to conjecture the substantially stronger version, which is polynomial Gyárfás-Sumner, which says that for every tree t, if you exclude t, then you're polynomially chi-bounded. Okay. So now let me just say a little bit about these two conjectures. So as far as I know, I think as far as I understand, the majority of people in chi-boundedness kind of believe that Gyárfás-Sumner is true. At least, we already have a list of evidence, right? A list of known cases, even though they come with very fast-growing chi-binding functions, but this conjecture seems to be believable. And the point here is the conjecture doesn't specify exactly what kind of chi-binding function that is. So it could be that the first proof is going to be using some sort of dynamical system or ergodic theory technique, which doesn't quite tell you what the chi-binding function is. Right? It only merely shows that the chi-binding function exists, but it doesn't tell you what the shape of the function is. And that would still be very nice, I think. But polynomial Gyárfás-Sumner is really a little bit too much to ask for, at least at the moment. So as far as I understand, at least we don't have any idea how to approach it, how to prove or to disprove it. Every approach, every attempt seems to be quite challenging. And there are actually more reasons behind this, which I will talk about later. And the second one is really a half structural and half extremal problem in graph theory. So on the one hand, you want to understand the effect of excluding a given tree as an induced subgraph. You would like to know about the global structure of excluding something which is a tree. Okay. And the extremal side is that you want to optimize the bound on the chromatic number. So if Gyárfás-Sumner can be regarded as a purely structural problem, then polynomial Gyárfás-Sumner is a half structural, half extremal problem, and seems to be completely out of reach. Okay, so given the state of the art on Gyárfás-Sumner, of course, poly Gyárfás-Sumner is still open, and given the state of the art on Gyárfás-Sumner on the known cases, we would kind of expect that known cases for poly Gyárfás-Sumner is also very limited. So what do we know? So until a few months ago, for polynomial Gyárfás-Sumner, this is basically the state of the art. So it was confirmed by Alex Goss, Bosimo, and Sophie Spurko 5 years ago that this is true if the excluded tree T is a double star, which is this configuration. So you start with a five-vertex path, and then you try to blow up each endpoint by an independent set. Okay. And in the literature, double stars are also known as trees of diameter 3, or trees with no P5 free trees. So from this sort of characterization, it would be very natural to ask, what about P5, right? So of course, maybe some of you already know that excluding P4 means that the graph is a co-graph, and so it is perfect, and so chi is equal to omega always. But what about P5? What about the five-vertex path? So in terms of history, you actually don't have to, know about this result just to ask about P5, because this was already in the problem list of Gyárfás from 40 years ago. So what Gyárfás wanted to do was to close the gap between polynomial and an exponential for chi-binding function when you exclude a path, an unreachable path. And the case P5 was singled out by Gyárfás. And then he wanted to get a polynomial bound, as far as I know. Okay, and this question, this P5 question, slowly became one of the most common open problems in the area. And so, for example, 10 years later, it was asked also explicitly by Kierstead, Penrice, and Trotter. And then over the years, there have been so many partial results and unsuccessful attempts towards this problem, just to decide whether P5 free graphs are poly time-bounded or not. So many papers and so many attempts. And yeah, in the next couple of slides, I will try to explain why people care so much about this very specific problem. So why P5 free graphs and what poly time-boundedness. Okay. Any questions so far? Right. So, so sorry. So this is just a slide just to convince you how hard people tried over the years to attack this polychi problem for P5. So basically, there were two lines of research. The first one was to try to improve the chi-binding function f, which was initially exponential until recently a quasi-polynomial bound was found by Scott, Simon, and Sperkel, and then in my PhD thesis, I managed to improve it a little bit more, still quasi-polynomial. And second, the approach was, so instead of just P5 free, you would like to exclude something else. And so, but perhaps the two most well-known cases are when first you exclude P5 and the house, which is P5 complement, and this was done already in the 90s. And then P5 and the bool, which is this configuration, a triangle with two bended edges attached to two different vertices. And this was done more recently. And interestingly, both papers prove the same bound for these two cases. But a particularly well-known question in the area was whether excluding P5 and the 5 cycle would actually give you poly time-boundedness. Yeah. So now we come to some reasons why people care so much about this question. So first of all, so we've been talking about time-boundedness as a way to formalize, as a way to control chromatic number in terms of clique number, right? And it turns out that poly time-boundedness indicates exceptionally good control over chromatic number. So clique number is essentially, the obvious bound on chromatic number. And if you mean the obvious lower bound, but what about the upper bound? If you can bound chi as a polynomial function of omega, then that means chi is basically collapsed to the same level as omega. At least from the complexity point of view, because we care about polynomial stuff, right? Polynomial functions. And so it was kind of a pipe dream in the area. So there was a question by Louis Esperet more than 10 years ago, which is to ask, okay, so could it be that time-boundedness and poly time-boundedness are the same notion? So it could be that they are actually equivalent. And okay, so as far as I understand, at least from what I heard from people in the area, essentially no one really believed in this conjecture at all. And Esperet also didn't believe in this conjecture, and what he wanted was to find a counterexample. And this is because, at least as from our understanding about chromatic number as a very hard to control quantity, as a very hard to control graph parameter, this seems very hard to believe. So, of course, it is not very surprising that this is false. But the surprising thing here is that you can actually construct a time-bounded class with an arbitrary growing, essentially arbitrary growing optimal chi-binding function. And this was done by Martin and Bartosz and James Davies a few years ago. So, which I really like. So this result is very surprising, I think. So it doesn't just disprove this supposed conjecture, but it also shows that time-boundedness is actually kind of wild. So what does it say? So it says that starting from any function f, satisfying certain condition on the lower bound, which is this one, you can actually construct a chi-bounded graph class G with optimal chi-binding function f. So here, what do I mean by optimal chi-binding function? So I start with a class G, which is chi-bounded. And then for every k, I collect all of the graphs in G with clique number, exactly k. And because the class is chi-bounded, I know that all of the graphs with clique number k must have chromatic number bounded by some absolute number, depending on k, of course. And I will define that to be fk. And so so this gives you, it gives a way to define the optimal chi-binding function for this class. And what Bartos and Martin and James Davies did was just simply to show that for any such function f, I can really construct a chi-bounded class G with optimal chi-binding function f, with this optimal chi-binding function. Okay. So not just that, there are classes of graphs which are chi-bounded but not poly chi-bounded. There are actually classes of graphs which are chi-bounded but not even exponentially chi-bounded, and so on. So if you give me any of your favorite function, sufficiently fast-growing, then I can give you a chi-bounded class whose optimal chi-binding function is growing much faster than your function. Okay. Yeah, and this shows that perhaps many known chi-bounded classes are actually not polynomially chi-bounded. And I think, so for example, Bartosz and Maciej probably know better about this than I do, because they've been trying to find more constructions, as far as I understand. And perhaps it could be that some natural chi-bounded classes known in the literature will need some super polynomial optimal chi-binding function. Okay. Oh, yeah, sorry. Yeah, and another point here is that it shows the fragility of polynomial chi-boundedness. It is not it is highly non-trivial, in the sense that if you want to get poly chi-boundedness from chi-boundedness, then you have to do much more. You have to dig deeper into the structure of graphs that you're working with. And this also explains why many current known results in the literature regarding chi-bounded classes would come with a super exponential chi-binding function. And this is just because perhaps we don't quite understand the general structure of the classes of graphs that we're working with. And also because in all of these arguments, in order to clean the structures, we have to use a lot of Ramsey type arguments, not just in the host graphs themselves, but also in the auxiliary graphs, where we need to construct in order to clean some more sophisticated configurations in our graph. Okay. So repeated Ramsey arguments and also perhaps induction on the clique number will together bump up the bound on the chi-binding function. Okay, so that's the first reason, which is with the notion of poly chi-boundedness itself. Second is with the class of P5 graphs from algorithmic and structural point of views. And somehow this class of graphs, the class of graphs with no five-vertex induced path, actually plays a pretty non-trivial role in these two areas. Right. So we've been talking about how to control the chromatic number in an exceptionally good way, right? We want to get a good grip on the chromatic number. So, of course, in general, it would not be very easy to say which problems are hard and which are easy and which are so-so. And if you want to talk about this, then perhaps a good way to say is through the lens of complexity theory. And so for instance, if you care about polynomial Gyárfás for the natural case of excluding a path, then actually P5 graphs play the role as the critical tractability boundary for coloring graphs with a covalent induced path. So what do I mean by this? So first of all, let me talk about the basic problem, which is k-coloring. Right? So I have a graph, I have an input graph, and then I ask, okay, so whether this graph admits a proper coloring using using at most k colors. Okay. Yeah, so there are two cases here. The first case is when k is also part of the input. And what is going to happen? Well, so for before free graphs, everything is in B, right? I mean, we know too well how they are constructed. You're just taking disjoint union and complete joint, starting from one vertex graphs, and then we're good to go. And so everything about before P graphs is in polynomial, I think. Well, but if you jump from P4 to P5, then this problem for k part of the input is NP-complete. So there's already some sort of jump in terms of complexity just by going from P4 to P5. Okay, and that's it. And of course, I mean for P6, P7, and so on, I mean you have the same NP-completeness phenomena. And what if k is a constant? So let's say that so now k is not part of the input anymore, but k is like 1,000. If you give, I mean, if I give you a graph which is P5 free or P6 free, and then I ask you whether the graph can be colored, can be properly colored using 1,000 colors, then what's going to happen? Well, so for example, if you remove P5 free or P6 free condition, and we just care about general graphs, then we know very well that 3 coloring is NP-complete in general graphs, right? So it's one of the basic NP-complete problems. Okay, so now going back to the excluding path business. Well, if k is fixed, then for P5 free it is in B. So there is a so there's some change in the picture here. If k is part of the input, then for P5 free it is NP-complete. But if k is fixed, then again for the same class of graphs, deciding is in polynomial. Okay, so in polynomial time, I can tell you whether any P5 free graph, any given input P5 free graph is colorable using 1,000 colors, and so on. Right, but what about P6? Well, already for 5 colors, it returns NP-complete. So as you can see here, there is some sort of message coming from the complexity theory, at least with respect to graphs excluding an induced path. And the message here is that perhaps for P5 free, okay, so it may be doable, but likely challenging. And the message here is that, let's say you want to do polynomial Gyárfás, you want to get a very good grip on the chromatic number for graphs excluding an induced path, then perhaps you should be able to do P5 free first before moving on. Okay, so that's explained. I mean, this offers another reason why, at least for polynomial Gyárfás and polynomially, P5 free should be looked at as a specific problem. Okay, right, and that was from the algorithmic point of view. So what about structural point of view? Well, one issue here is that there has been a lot of effort, a lot of work on trying to decompose these graphs. So I've thought about how to decompose P4 free graphs, right? They can be essentially decomposed into complete joins and disjoint unions and so on. But it seems perhaps very, very challenging to repeat the same thing, or at least to do some sort of decomposition for P5 free graphs. And this has been an issue in structural graph theory for the past 20 years. So this class seems to be very simple, but somehow, I mean, like, of course, it's just P5, right? But somehow, if you ask me to decompose every P5 free graphs into smaller graphs that are much more structurally restricted, then I mean, there is no known result in this sort of respect. And especially for polynomially, this seems to be an issue because most of the previous known polynomially results were done by some sort of decomposition techniques. So I can say, the strong perfect graph theorems, the class of graphs with no induced cycles of even length, circle graphs, graphs upon a clique width, and graphs upon a twin width. So all of them were done by some sort of decomposition. And the idea here is that you want to decompose into graphs that are much more restricted in terms of structure. And most of the time, you already know that those smaller graphs automatically satisfy polynomial 𝜒-boundedness. And then what's left to do is to try to analyze the decomposition type, how you decompose a graph, and then you want to show that those decompositions would preserve polynomial-boundedness, and then you eventually come to the main polynomial-boundedness result. Okay. Yeah, and this seems to be a real issue with P5 graphs because so far we haven't been able to do anything. Okay. Yeah, so that was the second reason. And okay, so now let me come to the third reason, which is what is perhaps more known in combinatorics and also a highly non-trivial problem, which is the Erdős conjecture. So this is a conjecture about Ramsey properties of hereditary graph classes. So we know very well from basics of Ramsey theory, right, that every graph on n vertices will contain a clique or independent set of size at least half log n. And recently it was improved to 1/2 plus epsilon for some positive epsilon. But the point here is if you don't care much about the constant factor, then that is essentially the best that you could do, because you can just take a random graph on n vertices and with H probability 1/2, and then with high probability, almost surely actually, the random graph will not contain any clique or independent set of size more than 2 log n. So in essence, if you only care about general graphs, then log n is essentially the best that you could hope for. But things seems to change dramatically as long as you forbid some sort of local structure in your host graph. So what the Erdős conjecture says is that as long as you try to forbid a graph H as an inducer graph in your host graph, then the bound on max of alpha and omega is going to jump from logarithmic to polynomial. So polynomial here means that you can always find a clique or independent set of size at least n to the c, where the power c depends only on the graph H that you're excluding and nothing else. So this is still very much open, and perhaps this is one of the most well-known open problems in all of graph theory and combinatorics. And recently there's been some progress. Yeah, and as I said, this could be interpreted. This conjecture can be interpreted as diagonal Ramsey with additional structural constraints. Okay. Well, and actually, from the point of view of polynomial 𝜒-boundedness, then Erdős is just a baby step. So no matter how supposedly difficult Erdős is, if you have a graph class which you want to prove polynomial 𝜒-boundedness, then Erdős should be the first step. And perhaps Erdős should be looked at as a toy case. And the reason here is because of this chain of inequalities. So polynomial says that there is some positive d depending on the graph class that you started with, such that omega to the d is at least chi, right? And there's also a very trivial inequality coming from the definition of chi and alpha. That is, chi is always at least n over alpha, right? Because chi just basically partition into independent sets. Okay. And if I combine these two inequalities, then what I get is going to be alpha times omega to the d is at least n. And because of this, and say that max of alpha and omega is at least n to the 1 over d plus 1. So of course, polynomial implies Erdős in a very strong way. Okay, so now let me go back to the case of classes of graphs defined by excluding just one inducer graph. So what do we know about this? Well, Erdős is conjectured to be true for excluding any given small inducer graph H. So what if I ask for a similar property with this inequality instead? Well, then it turns out that if I'm H-free, just H-free, and I'm asking for the middle inequality, then the graph H that I'm excluding must contain no cycle. And this is just because of the probabilistic construction of Erdős. I mean, if you look at his paper, or if you look at the book of Allen and Spencer on the probabilistic method, then you will see that actually what Erdős proved was, for every G and for every sufficiently large n, you can find a graph G on n vertices with no cycle of lengthless G and with alpha properly sublinear in terms of n. So there is a gap here, which is n to the 1 minus 1 over 2G, okay, approximately. And so if we try to plug this observation into this middle inequality, then you will see that the excluded graph H must contain no cycle. So this is the same reason why the Gyárfás conjecture would be, I mean, if true, would be if and only if for excluding a tree or a forest. Yep. Yeah, so already at this stage, if you want to move from Erdős-Hajnal to this middle inequality, then you really have to use the fact that you are excluding a graph with no cycle. And if you care about the case when H is connected, then you must use the fact that H is really a tree. Okay. And then, of course, I mean, going from this middle inequality, this off-diagonal Ramsey form, to polynomial-boundedness is going to be even more challenging because at this point it is going to be about chromatic number. Okay. Yeah, and the point here is that so far for most of the known polynomial boundedness results, we have a relatively simple proof for Erdős-Hajnal. So it is not, as far as I understand, it is not very hard to verify Erdős-Hajnal for the graph classes of interest. And with much more sophisticated ideas and proofs, you can get polynomial-boundedness. But I mean, you have to really use the structure of the graphs or the excluded graph that you want to work with. Right, and so far for, I think, as far as I understand, for all of the confirmed cases of Erdős-Hajnal, so far, incidentally, P5 was also objectively the most challenging case. And so from this point of view, we could see that perhaps polynomial-boundedness for P5 should not be very easy. Okay. Right, so the main result that I want to talk about today is the one that came out around 5 or 6 months ago. That is, yeah, this true that P5 free graphs are polynomial-bounded. So yeah, so I will try to speak a little bit about some proof ideas. I think I actually have 30 minutes, right? Yeah. Right. Questions? Right. So just in case you're interested, so before that there was the Erdős-Hajnal results for excluded P5, which was done by Alex Scott and Cosimo and myself. And perhaps you would ask, okay, so whether this would give a new proof of Erdős-Hajnal for P5, and the answer is no, because it uses Erdős-Hajnal as an input. So the proof is basically done by bootstrapping Erdős-Hajnal for P5 into polynomial-boundedness. And it is really an important part of the proof, and if you remove Erdős-Hajnal from it, then likely the proof will break down. So far we only have one proof of Erdős-Hajnal, and there's a way to connect Erdős-Hajnal with polynomial-boundedness. And hopefully this pattern will be repeated for longer paths like P6 or P7, but I haven't been able to do it. Okay. Right, so that's the first remark. And the second remark is about the main idea behind the proof. It is not just Erdős-Hajnal, but it is about something else. So in order to prove this, I try to implement a new framework in time-boundedness, and I would like to call this chromatic density. And the idea here is that we would like to view chromatic number as some sort of a function or a measure in the host graph satisfying certain axioms. And then we try to understand how the structural constraints on the host graph will influence the chromatic distribution in the host graph. So how chromatic number would behave for different induced subgraphs of the host graph under the structural constraint. Okay, and here there are all of the properties of the chromatic number that I use in this proof are going to be about these three properties or three axioms. Just for convenience, I'm going to say that any function satisfying these axioms is called a measure. I mean, for the lack of a better word. Okay, so mu from the vertex, I mean the set of vertex subsets of any given graph G to the positive reals is a measure on a graph G if it satisfies the following three conditions. So first, the mass of every vertex is exactly 1. So just like a uniform condition. The second condition is that the maximum measure of any two sets A and B is at most the measure of their union. Okay, and this implies that this measure mu is monotone with respect to inclusion. And here, in this case, you have equality if G contains no edge between A and B are disjoint. And in this case, in the literature, it is also known as A and B being anti-compete to each other. And the third condition is that for any two vertex subsets A and B, the sum of the masses of A and B is going to be at least the mass of their union. Okay, and again here equality holds if A and B are disjoint and compete to each other, and in the sense that A and B form a complete bipartite graph in the host graph G. Okay, yeah, and it is not hard to check that chromatic number satisfies all of these conditions. And here I am conflating vertex subsets with induced graphs. Yeah, so chromatic number is a measure. And actually, it is not hard to see that not just chromatic number, but many fundamental and well-known graph parameters are also measures. So the clique number, the fractional chromatic number are also measures on G. And with a bit more thought, you can see that actually any measure is bounded from above by chromatic number and bounded from below by the clique number. So this is kind of convenient because if our argument works for any measure mu, then it would automatically work for chi, of course. And if we can bound chi as some function, and in this case as a polynomial function of omega, then the same holds with chi replaced by any measure. So this sort of thinking is kind of convenient because we now don't have to care about well-known tricks for graph coloring. For example, going through degeneracy or trying to do product coloring or anything similar. We only have to care about these three properties, and then we try to understand how chromatic number would behave under the structural constraint. Yeah.
Sorry, I think I'm failing to understand why, let's say, mu equal to just the number of vertices in your subgraph is not a measure.
It is not a measure because of this equality condition.
Oh, we don't say they don't need to be disjoint.
No, but equality, right? Equality means that one of mu A and mu B is equal to mu A union B. And if A and B are, yeah.
If A and B are disjoint, it is not.
Yeah, so, yeah. Right?
That's true. Yeah, that makes sense.
Yeah. Any other question? Right. Yeah. So that's basically how the proof goes. And actually, the proof is just going to be about chromatic number satisfying these three properties and nothing else. And the use of the clique number is minimal. If you look at the paper, then almost nothing is about the clique number at all. Just about chromatic number. Okay. Yeah, so there are actually several ingredients in the proof and how to make this idea work. So there's actually a whole framework which is still developing, and I will try to go through each of them and try to speak about the motivation. So the first idea is chromatic quasirandomness. So in case you're already familiar, quasirandomness is a kind of way to classify. Is a way to say is a way to classify the properties of graphs that behave like a random graph, right? And there are many equivalent definitions of these of these properties. And one of them is just like if your host graph is not being very close to a random graph, then you are going to contain many copies of any small inducer graph. Okay. And this idea is formulated by the following result of Erdős from 1986, 40 years ago. So given any excluded graph H and any density parameter epsilon, I can find some delta depending on H and epsilon only, such that if my host graph G is H-free, then there's going to be an inducer graph. Here ISG means inducer graph F of G with at least this many vertices. So here this notation, absolute value of F just means the number of vertices. So F has at least this many vertices, and either F has max degree at most epsilon times F, or F has mean degree at least 1 minus epsilon times F. So what this basically says is that if you're H-free, then you're going to contain an inducer graph with linear size, linear number of vertices, which is very sparse or very dense. Okay, but of course means sparse and dense here are all in traditional sense, which is by counting vertices and mass and mean degree. So here's the picture. Yeah, so this in the sparse case, the neighborhood of V of every vertex V in F has more number of vertices, and here this is the dense case, which is every vertex V has non-neighborhood of small size. Okay. Yeah, and this has been very useful in recent progress on Erdős Hajnal. And and the reason why it has been useful is that, especially if you care about excluding the graph H, which is a tree or a forest, then we are coupled with a very useful result of Chernovsky's Cosimo circle roughly 10 years ago. And what it says is that if you don't contain a given tree as an inducer graph, and you are sufficiently sparse in this sense, which is exactly this condition, then you're going to contain two disjoint and anti-complete vertex subsets, each of size at least epsilon times the number of vertices. So basically, this is known as the trees and linear anti-complete pair result. If you're sparse and you don't contain a given tree T as an inducer graph, then you are going to contain two linear size anti-complete pairs. So it's two linear size anti-complete vertex subsets. Okay, right. And if you apply these two results, if you try to combine these two results for graphs with a forbidden induced tree, then what you get is going to be something like this result, but now with the second outcome. So with the first outcome replaced by this linear anti-complete pair conclusion. And again, formally, for every epsilon and for any tree T, there's some delta depending on T and epsilon only, such that if I am T-free, then either I contain a pair of linear size and a complete vertex subset, or an inducer graph of linear size and is very dense. Okay. And for Erdős Hajnal, this was useful because the first outcome would give an independent set of polynomial size almost immediately through induction. And so all the focus will be on the second case, which is the main difficulty. Yep. And the first idea of chromatic quasirandomness is to try to formulate an analog of this theorem for graphs excluding P5, and hopefully we'll see more of this in the future for excluding P6 or P7 or any PT anyway. Yeah, so the first outcome is not very hard to formulate. You can just replace the size by the chromatic number, and that would be nice. But the hard point is to try to formulate the right notion for density with respect to chromatic number. And here's a candidate which has been quite useful. So for every epsilon, I'm going to say that G is epsilon chi dense if the chromatic number of the non-neighborhood of every vertex V in the graph G is going to be less than epsilon times the chromatic number of G. So what this means here is that if I pick any vertex V and I try to get rid of all of its neighbors in the graph G, then what I get is going to be something with much lower chromatic number. Okay. All right. So this definition seems a little bit unnatural, and of course, if you try to compare this notion with this traditional high density notion with respect to counting, then it is not very hard to formulate, to construct examples where graphs which are dense in the traditional sense can be very far away from being dense in this chromatic sense, and vice versa. There are also graphs which are dense in the chromatic sense, but not dense in the traditional sense, like this. So to see the second, you can just take any complete multipartite graph with very unbalanced parts, right? And they're of course dense in the chromatic sense, but as long as there is one part whose size is significantly bigger than the other parts, then this graph is not going to be dense in the traditional sense, and vice versa. You can also start with a complete multipartite graph where every part has equal size, and then you try to place smaller induced subgraphs inside each part with varying chromatic number, and then you'll be able to construct graphs which are dense in this mid-degree sense, but not in the chromatic sense. I'm not going to detail. So in other words, these two notions in general are very different. And so working with this definition means that you have to think about density in a different way. Okay, right. So so now I'm going to plug this notion into the second outcome. So what it says is that for every epsilon, there's some delta, such that if G is P5 free, then either I can find an anti-complete pair of vertex subsets with linear chromatic number, or I can find an epsilon chi dense induced subgraph with linear chromatic number. And linear here means at least delta times the chromatic number of the host graph G. Okay, so this is true. And somewhat surprisingly, the proof uses the Gyárfás path argument. So Gyárfás path is a very interesting technique that shows that if you have a graph with no long induced path, then you're going to contain a vertex whose neighborhood has linear chromatic number in the host graph. And so this was done by Gyárfás, and what he showed was something like this. And this is true for pk3 instead of p5, instead of just p5. And the key thing here is that we always have this linear constant factor. And this is the very reason why this lemma can be proved, at least for now. But so far, I haven't been able to prove a similar result with this notion of epsilon chi density for pk3 graphs in general. And one of the first open questions is whether this can be extended to pk3 graphs. It will be very interesting, but so far, I haven't been able to do so. Right. So I think I have 15 minutes left. I think I have 15 minutes left.
Yeah, take your time.
Yeah. Right. Okay, so that's the first one. And the key intuition behind this result is that if you don't contain P5, then the chromatic distribution of your host graph is going to be very far away from randomness. Okay, very non-random. So instead of H distribution, we are going to say about chromatic distribution. Okay, and an even more overarching goal would be to try to extend this not just to pk3 but to excluding any tree. It would be very nice. But, I haven't been able to do so. Okay, so that's about this lemma. And now we'll try to see how this lemma could be useful for for the case of trying to get polynomial 𝜒-boundedness. Okay, so one thing here is that polynomial 𝜒-boundedness says that if you have a graph with large chromatic number and excluding P5, for example, then you're going to contain a clique of size polynomial in the chromatic number. So in other words, we're going to contain a huge clique, right? So in this sense, the second outcome seems closer to the actual conclusion, right? Because complete graphs are, of course, dense, and here we can somehow isolate the graph into a very dense core. So the second outcome should be kind of closer to what we want to do. But the first outcome seems a little bit, of course, it looks very, very natural, I think, because anti-complete pairs might come up everywhere. But the main issue here is that for chromatic number, having anti-complete pairs is very hard to work with because chromatic number remains the same under disjoint unions, right? Right. So in other words, so first of all, chromatic quasirandomness says that if I'm P5 free, then either I'll have a linear chi anti-complete pair or a linear chi dense inducer graph. And as I said, the second outcome is supposed to be useful, but the first outcome, even though natural, seems kind of useless. And the reason why this is useless is just because chromatic number is closed under disjoint union. It stays the same. Okay. So what are we going to do now? So I've been talking about decomposition, right? One of the ways to approach polynomial 𝜒-boundedness is to decompose the host graph into smaller pieces, into simpler pieces. And okay, so at this point, to be honest, I haven't been able to decompose P5 free graphs in any definite way. But what I can do is that, okay, so let's say that if I'm trying to isolate my original problem into essentially one typical case of chi-dense inducer graph, which is also closer to having a large clique, then what can I do with these linear chi anti-complete pairs? The point here is I can assume that these linear anti-complete pairs are everywhere. They crop up everywhere around my graph, and what I'm going to do with them. And this led me to the second idea, which is to decompose my whole graph using these anti-complete pairs. Okay? Yep. And so basically, that's just what I said. I would like to decompose my graph using these anti-complete pairs to reduce the problem into chi-dense inducer graph. And the assumption now is that if I pick any inducer graph of my host graph G with a linear chromatic number, then I'll be able to see two linear chromatic anti-complete subsets in that inducer graph. Okay, and this turned out to be quite useful if the host graph is P5 free because of this reason. So let's say I start with two sets A and B with no edge in between. Okay, and of course because I'm doing chromatic number, I may assume that the subgraphs of G induced on A and B are connected. Okay. Yeah. So, and I can also assume that the graph G that I started with is connected because I'm doing chromatic number. So here's the observation. If there is some vertex V outside of A and B with a neighbor and a non-neighbor in both A and B, then I'll be able to get an induced P5. And here's the reason. So first of all, V has a neighbor and a non-neighbor in A, and A is connected, right? Now look at the set of vertices in A, non-adjacent to V, and the set of vertices in A adjacent to V. These two form a partition of A, and because A is connected, there has to be an edge between them. So I can find two vertices adjacent and in A, such that one is adjacent to V and the other is non-adjacent to V. Okay? And similar reason for B if V is mixed on B as well. Yeah, and these 5 vertices would give me an induced copy of P5 because I assume that A and B are anti-compete at the beginning. Okay. So what do I do now with this observation? So I go back to this picture and I have A and B, and I'm assuming that G is connected. So the fact that A and B have no edge in between and G is connected means that there has to be a minimal non-empty cut set S separating A and B in G, right? So the minimality of this cut set S will mean that every vertex V in S has a neighbor in both A and B, right? And of course, by enlarging A and B, if necessary, I can assume that A and B are actually 2 components of G removing S. So what's going to happen now? So from the previous observation, every vertex in S cannot be mixed on both A and B. And since each such vertex has a neighbor in A and in B, it turns out that every vertex in every vertex V in S is complete to A or B in G. Okay? And so I can partition S into 2 sets, SA and SB, such that SA is complete to A and SB is complete to B. Right? So what am I going to do with this observation? Okay, so the point here is that I'm given these linear chi anti-compete pairs everywhere in my host graph G. And I can assume that A and B have linear chromatic number in terms of G. And here I am assuming that the chromatic number of A is at least that of B, and at least delta times the chromatic number of G for some delta sufficiently small, but it's still a constant. Then from this observation on the right-hand side, I can conclude that one of the 2 following cases must occur. So either the chromatic number of S is actually low, or I can find a complete pair with large chromatic number, with linear chromatic number, right? So suppose the second outcome doesn't hold, then because I know that chi A and chi B are already at least delta times chi G, I know that the chromatic number of SA and the chromatic number of SB have to be at most delta times chi G. And so now I can use sub-additivity to conclude that the chromatic number of S is at most 2 delta times chi G. Okay? Right. So what am I going to do with this observation? That is, I already have a very low chromatic cassette. Well, at the beginning, in this case with A and B, I have the complete freedom to choose what A and B are, and especially among the components of G removing S. I can actually choose A and B to be the 2 components with the largest chromatic number. So, in other words, A is going to be the component with the largest chromatic number among any other component of G removing S. And what is going to happen is that actually the chromatic number of A is not just at least this delta times chi G, but actually at least 1 minus 2 delta times chi G, right? Because chromatic number is invariant under disjoint union. Okay. Yeah. So in other words, I have been able to turn something like linear versus linear for anti-complete pair to linear, which is for B, to almost 1, which is the case of A. And now I would like to repeat the same sort of argument inside A, and then I keep decomposing the graph until I get something. But of course, it is getting more and more technical, and I'm not going to say much more about it. But the goal here is to try to say that, so not just I can force A to have chromatic number close to chi G, but I can do the same thing for B as well. So at the end, I'll be able to grow these linear anti-complete pairs so that the chromatic number got very, very close to chi G. And I want to say that if I cannot do this sort of growing business, then I can actually capture a polynomially chromatically dense induced graph, whatever that is, but it's sort of closer to what we want. And just one small remark here is that this complete pair outcome will actually give this kind of thing, but the things are going to be a bit numerical. So yeah, so that's basically the idea, and that's the second part of the proof. Okay, so what I have said so far is just going to give you some sort of an idea of how the argument works. And the previous two ideas basically has the real goal is to try to isolate the problem into essentially one case, which is when the graph is chromatically dense. And that's the main business of the third idea, which is the most technical one, and I'm not going to say much about it. But this is called chromatic density increment. So this is mostly inspired by recent progress on Erdős Hajnal. But the idea here is something like this. So given a graph G, which is epsilon chi dense, chromatically dense, I would like to show that there are two universal numbers, A and B, such that for any G, which is epsilon chi dense, I can find an induced graph f of G, which is epsilon to the A chi dense and with chromatic number, at least this. So there's some sort of polynomial trade-off between the chromatic density and the shrinkage factor in terms of chromatic number. And if this cannot work, then something else has to happen. Okay, some other nice things have to happen, and in the case of P5, this come up in several configurations, which again I'm not going to talk about because of time constraints. Okay. Yeah, and the argument is modeled after something called specification for Erdős Hajnal for P5, and so specification has been very useful in recent progress on Erdős Hajnal, not just for P5 but for other cases like DC dimension, and yeah, but especially in this case, the proof of this is modeled after specification for P5, and then you do 2 rounds of this kind of thing. And one issue here is that for Erdős Hajnal and for basic counting in general, we have the luxury of doing double counting or random sampling for basic argument. Everything is kind of nice because it's just counting vertices. But chromatic number is a lot harder to control, and it doesn't work very well with counting vertices. So even though this idea was modeled after specification for Erdős Hajnal for P5, the actual detail is substantially different. So it's still basically about running 2 rounds and then keep going. But because it is chromatic number, much more things need to be addressed. And again, I'm very sorry that I cannot tell you more about it. And that is also where the Erdős Hajnal probability of P5 can be, because to handle issues involving counting with chromatic number and to handle the structures more carefully, I gotta use Erdős Hajnal for P5. And of course, with more structural arguments involving the five-vertex path. So these are all workarounds, right? And yeah, I think that's the end of the talk.